Hi, friends of the sun. Welcome to our weekly reading group every Monday happening here on Zoom. You can find all the links in the description to join that stuff. And today we have Lior Yariv, I think it's pronounced, and she's talking about Mosaic-SDF, which is like a new 3D representation, and they made that specifically for generating 3D shapes. And yeah, let's go.
Okay, so the paper that I will talk about is called the Mosaic-SDF, or for 3D generative models. And as I said previously, this work was done as part of an internship I did in Meta with this amazing collaborators. And I will present also this paper in the upcoming CVPL. So the big question that we had in this paper is how can we build a large-scale 3D generative model? Are we all aware of like large LLM models, like large language models, and like 2D image generative models? But I would say that like 3D generation is not in that same scope yet. So this was kind of like the question that led us and guided us through this paper. So just like a quick recap overall of generative models in general. So the idea that we have, the main idea is that we have a source distribution, which is a distribution that is easy to sample from, like for example, like Gaussian noise, and we have a generator function that take us from this source distribution to a target distribution. And here, for the example, we go back to maybe 2D images, which is more common and well-known. And let's say, for example, here, the target distribution is like natural images. So specifically, we're going to focus on a certain family of generative models, which are diffusion or flow generative models. I will refer to those, to both of them as like kind of like equivalent, because they have the same idea of how we want to train them. And the idea is kind of like illustrated here in this slide. So the idea is that we take one sample from the source, from the source distribution, so the noisy sample x0, and we take one sample from the target distribution x1. And we can look at an intermediate step using a predefined path, noisy path that we defined between them. And the path is changed whether you use diffusion or flow, but we won't get into this details right now. We just want to understand the high-level concept. So we have x3, which is the intermediate step. And our model wants to predict the learned model that we want to learn. And what we want to predict is the next step towards the noise version of this image, meaning towards x1. Okay, so we train this theta t according to different source distribution samples and target distribution samples, like data samples, and across different time. And once we train this model and learn such model, we can now sample a new sample from a model by just like solving across time, and do that iteratively by starting and sampling a noisy image, a noisy x0, and gradually apply step by step the learned model until we get this clean new image. Okay, I guess we don't have questions so far, because this is pretty something that I guess you most of are familiar. But now comes the question, okay, everything is nice and all, and we know how to apply diffusion and flow model for images, but how can we apply that for 3D data? So again, if we examine the idea behind images, the main question is the data and how we present it. Okay, so in images, it's pretty straightforward. We have image data. It's given us as a 2D resolution grid, 2D grid, like with some certain resolution, and it is given as is. If you want to, I don't know, upscale, descale, whatever, to get like with the proper resolution, but it's very straightforward that this is your tabular tensorial data that you have in mind and that you can work with. And according to the data representation, you can also choose a specific model that you want to train with. So for example, with images, people are using convolutional neural network, or specifically the architecture of UNet. Some people now are starting to use transformers, but this is something that is well known and common to work well with this type of 2D grid data, yes. What about 3D shapes? How we represent 3D shapes? So the data of 3D shapes is basically come as meshes or triangular meshes, which is not very unique and unified across all the shapes, right? You have different numbers of vertices and faces. The topology can be different. You don't have like one unique and unified way maybe to represent this shape like you have in images. And like the type of representation for these 3D shapes is not very straightforward as in images. And also the question of the model which you use gonna be affected by this 3D representation that we're gonna choose, because we want this model to be kind of like compatible with this data representation that we have. Yes.
So now
you don't have to maybe point. You can just like even just like interrupt me. It's also fine.
Yeah.
Yeah.
So now you said something about like the vertices. A number of vertices is not the same. We have rough edges or something in that direction. But doesn't all of this also hold for image data? And we just increase our resolution to the point that we are able to deal with all of those sharp edges and different number of or different
Yeah,
that occur in
definitely, but it's like the differences are much more. You know, the 3D data is usually come from I don't know, artists who kind of like doing synthetic 3D shapes and meshes, and it can be very, very different. It's like it's not a different of like 128 by resolution to 1000 or something like that that you can downscale and upscale simply. It can be, I don't know, million vertices compared to 1000 vertices. And also the way to do like upscaling and downscaling in vertices is not straightforward as it is in images. So I would say it's not like a straightforward like to get this 3D data in a unified mesh representation choice.
Okay, I want to chat a little bit more later about this, like just voxelizing stuff, basically. But let's continue for now.
Okay. Okay. So with this kind of like question and the concept that we maybe have from images, we wanted to design design principles for the 3D representation that we're gonna use for our generative model. So keep in mind that this design principle for the 3D representation is for a model that its goal is to be served as generative. So the first thing that is, again, maybe a bit more straightforward from images, we wanted to have a simple tensorial structure like we have for the 2D grid for images, and we wanted to be compatible with known expressive neural architecture like convolutional, transformers, and so on. Like something that we want that we know that works well. The second principle is that we want the preprocess of taking one mesh to its representation will be efficient, right? Because we want it to be as much as efficient that it can to be, because we want to compute this representation for a large collection of shapes. And the last principle that we want to have in mind is we want it to be efficient in terms of parameters. So unlike images, which kind of like occupy the full 2D grid, if you think of 3D shape, it's only occupied in like near the surface, right? So you can think of it as like, how can you make a representation to be efficient in terms of a good trade-off between the approximation of the shape and the parameter count. So you see the front example here on the bottom right, like the left one. So both representation have the same number of parameters, but the left one is represented less good, like it has a worsened approximation for the original shape than the right one, right? Because we don't have all the details. So before we jump into this representation and like type of representation, and maybe also define the representation that we suggest as so one of the very popular approach of representing 3D shapes is using implicit representation. And I want to kind of like explain it to you in high level here. So we jump to just like to the 2D case, like representing like simple 1D surfaces. So we want to represent this surface as a line, and we do that using implicit representation. And the idea behind implicit representation is to define an implicit function that is, for example, negative from the inside, positive from the outside, and then it's only 0 on the surface itself. And in that sense, we say that we represent this surface implicitly as the 0 level set of this function, meaning all the points that is 0 given this function. Okay, so this is a continuous representation that is become, again, very popular in the recent year. And one of the choices that one can make for such function will be a sign distance function. So the sign distance function depicts for each point in space its signed distance to the surface. So you can see that the red level set, the red contours are kind of like the positive distance to the surface, and the green one are negative distance to the surface. Okay, and this one will give us a very nice way to define the surface, again, as the 0 level set of this function. Yes.
And this now sounds like you're doing more than what we actually need, so to say, right? We have our surface, and now we could either just say where is the surface, or we could always say where is the surface and what is the distance to the surface. So aren't we like doing more than we need and getting a less efficient surface representation?
Yes and no, because you can think of so first of all, this type of representation have a lot of good values. For example, given this representation, you can extract a surface out of it by just like extracting the 0 level set, right? And you can think of that you don't like the global far away information is not really matters. Like what really matters is like only in the vicinity of the 0 level set, right? So you just like need to know where you're crossing between positive and negative. So it is okay if you have only information like around the surface. And like given a mesh, it is like given a mesh, it's mostly very, there is a way to kind of like define a sign distance function according to this mesh. Okay?
Yeah, okay.
But like something that is important to note about this representation is that it is a continuous representation, right? It is a continuous function, and we need to discretize it in some way in order to represent it and to use it as like a tensorial representation. So there have been several ways of common 3D implicit representation that people have been used for as the representation to use for generative models. And we're gonna examine some of them and also examine how they kind of like agree or disagree with the design principle that I mentioned before, which are again, like the efficiency of the preprocess, the parameter efficiency, and the tensorial simple structure that is compatible with different and known architecture. Okay, so the first, so we will examine that given maybe this car ground truth. This is our mesh, our input, And as I said before to you, Hans, is that given the mesh, we have a way to compute the true sine descent function to this mesh. So the first 3D representation that we can use, again, we want to represent the implicit function using some distinct option. And the first one is maybe the most naive choice that is coming from images, is instead of like representing the SDF as a 2D grid, representing like a 3D grid. Okay, so think of like storing some SDF values on the grid, and in order to evaluate some specific point function, we can do trilinear interpolation across these values, and then we get the implicit function evaluation, the implicit SDF value according to that one. Okay, so let's say we have some budget of around 350K parameters, and we want to approximate this car, and this will be the result of approximating this SDF to the car using a 3D grid with some budget that we have in hand for this. So in terms of preprocess, it's very efficient. Think of like as in images, right? We just need to store the SDF values on the voxels of the grid, like sampling an image or something. That it is very efficient and can be done in like half a minute. Its structure is very simple. It's like a 3D grid, and you can use, I don't know, 3D convolution, and everything that is basically done for 2D images can be applied here for this 3D grid. But in terms of the trade-off between the approximation and the parameter efficient, you can think of like you have a lot of redundancy voxels that they are not like store any information that is required, right? Because you only have information around the surface itself, and that is why it's very not parameter efficient in that sense. And because of that, people kind of like try to improve this representation and suggested the three-plane representation. So the three-plane representation is just like, you can think of like a compressed version of the 3D grid. And now in order to evaluate the implicit function in a 3D point, you first project it to each one of the plane. So we have 3 planes for X, Y, and Z for each one of the axes. And given this projected point on the plane, we apply bilinear interpolation according to some 2D grid values that we have now. And then we combine these 3 evaluations according to each one of the planes in some way. We can do summation or concatenation or something like that. And this will give us the final function, implicit function evaluation. So instead of just like doing a cubical grid, we have now 3 2D grids.
You could also
okay, so
like 4 or 5 or 10 2D grids, right? And take
yeah, I don't know, but this is like so think of like you don't have like one channel on like one value on each one of the planes. So usually you have like multiple channels on each one of the planes, and then you can store more information. But I think this was like the most simple, and I think that people thought about of like doing this 3 axis aligned grids. Yeah, so just like some like a low rank projection of the 3D grid into 2D planes.
Yeah, I guess 3 is the lowest number that you can use to assign something unique to every point. No, I don't know.
And also there's like a very easy way to project a point to these planes also, I think, because it is like the idea of like evaluate this function very fast.
Yeah.
So again, given the same parameter budget. This is how this SDF to the car will look like. You see it's a bit more noisy because it has a little bit more degradation that need to further regularize. But in terms of pre-process, you can think of it as still efficient and can be done in 6 minutes. The structure is again simple, is to the grids, right? So you can apply the same thing as done for images, which is to the convolution or even transformers and stuff like that. But again, in terms of parameter efficient, is very similar to the 3D grid because it is a voxel-based representation, right? And you're gonna have a lot of redundancy in this representation again. So, and the less representation is another common one that I don't know if you're familiar with, but it kind of like gained a lot of popularity in the recent years, that it's called implicit neural representation. And the idea is to represent a function, an implicit function specifically, using a fully connected neural network or an MLP, and then you can evaluate a 3D point, like using a 3D coordinates, and then output the function, the network evaluation of the SDF used for that point. Okay. So this is gonna give us maybe a better approximation for this, because you don't have like a lot of information that is stored in empty voxels, right? You can only store information of the surface within the weights of this neural network. So it is parameter efficient, but in terms of pre-process, it can take 30 minutes and even more. And its structure is a bit more complicated, and it has some symmetries that it's not very, maybe I would say, straightforward to understand how can we model these symmetries of the neural network and take it into consideration when you take, I don't know, some model, transformer model for these weights.
So your neural representation then here wouldn't be what we typically have in a nerve, where we're representing some density or something like that, but it would be again just the distance to your surface.
Yeah, so you can think of like a nerve, but instead of representing a density or a view-dependent color, you represent, given a 3D point, you only represent the sign distance function to the shape. Yes.
Okay.
So these are kind of like some of the representation that people have tried to build upon. This is like a known 3D representation that people use for reconstruction and other kind of like application, and also people have been using them for 3D generative models. But because that we have this 3D design principles in mind for that is like geared towards 3D generative, we thought like, okay, this representation is, this known representation are not good enough, and we need to kind of like came up with a new representation that will be better suited for 3D generative models. So for that reason, we introduced a new representation that is called Mosaic-SDF, or M-SDF in short. And the high-level idea is that we want to represent the surface as a set of volumetric local functions that is kind of like stored and located on the surface itself. And we will go over the representation explicitly, and I will explain it. And like you can see from the right, this is kind of like how we draw this representation. Maybe we'll give you some high-level concept of what this representation means. But in terms of the design principles, as you can expect, it's kind of like suited, fit for all of the design principle that we kind of like had in mind. So it is efficient in the pre-process. It takes only 1 minute. So it is efficient in parameters. So this is the reconstructed car with the same budget as I showed you in the previous slide. And you can see that it has the best trade-off between like the parameter budget and the approximation power. And it is has a simple tensorial structure that is compatible with the transformer architecture that we will use as our generative model. All right, so let's go inside to the M-SDF representation, and I will explain to you what it is and how it works, basically. So again, we're back to 2D because sometimes it's easier to draw surfaces and stuff and illustrations in 2D. So the representation, as I said before, it's a set of voxels, of volumes that are stored around the surface. And these volumes are represented using these three variable tuples, where the first one is the centers. So we have the center of each one of the local volumes, which is basically a point in 3D. So PI, as you see here from the example from the right, they're just like points that are like in space. SI is the scale of the volume. You can think of like the L1 radius of this volume, basically how big this volume is, and it can be varied and can be like wider or smaller, as you can see again from this example from the right. And these centers and scale kind of like define for us the local volume, but we want to also kind of like describe the local function, the local SDF according that is live within these volumes. And we're gonna do that like using a local grid. So think of like the 3D grid representation that we have for the global SDF function, but now it only defines this simple patch, this only surface piece here. So another way to think about our representation is that I like to think of as like if you have images and you need to patch them. So think of like our representation is a way to kind of like patchify the surface using small volumetric grids, but it has a bit more versatile options because it depends on like where you locate the surface, the centers, and also the scale of each one of the volumes. So I will just like maybe repeat on that. So the VI are the values that are stored within this local grid. And again, you can think of like a patch of SDF values within this local neighborhood. And the local grids are all with the same resolution, and it can be very low resolution. It's basically a 7 by 7 by 7 local grids. I think someone have a question?
Yeah, so PI is a single value. VI are like the VI are n by n by n numbers, and SI.
Okay, so PI is a position, so it's XYZ. It's a point in 3D, right? It's a center, so it is like 3 values. SI is one scalar value, and VI is a grid, so it's like M by M by M. Yeah. So say I have a local grid of 7 by 7 by 7. So each volume is like 7 by 7 by 7 plus 1 plus 3. And this is the number that I have like the number of variables that I have for one volume. And overall, I have like 1024. This is like, for example, the parameters that we use, but let's say I have like around 1000 volumes. Another way to think of it is like if you are more familiar with the point clouds, so think of it as like featured point clouds, right? So you have a point cloud, but instead of just like storing X, Y, Z, we also store a local neighborhood function, local function that describe the kind of like surface around this point cloud. Okay. Yeah. I see there's like another person that is raising a hand, or I'm not sure.
I have a question regarding this. I'm just trying to make the link with the equivariant models, and I'm wondering if this representation is equivariant because it's using the coordinates.
Yeah. So the question is equivariant with respect to which symmetry. So if you think of like the permutation equivariance, so it can be equivariant same as you have point cloud equivariance, right? So it is a set, and we don't care about the order of the volumes.
Okay,
so
so it has
this,
the same. Oh, sorry.
no, yeah.
So it has the same equivariance properties as point clouds. So no equivariance
Yes.
to rotation or translation. Okay.
Yeah, so translation and rotation, no. We can maybe discuss in the end of like other ways of thinking of like how adding like rotation ones. Translation, you know, if you just like take the full data set and kind of like shift it to be you know, with like all of them, like the mesh is like centered in the origin and kind of like scale to be covered by the unit sphere and the unit cube. So you kind of like lie like all the data sets kind of like lie in the same regime. But the rotation equivariance here is a bit more interesting, I would say. Yes, and maybe at the end I will have some note about that.
Okay, thank you.
Yeah, you know what? Maybe I can say even something now. So think of like the local volumes right now are axis aligned, right? So another thing that we can add for this representation in maybe is like a local frame of like how your representation is, each of the volumes is kind of like rotated in space. So if you add this another degree of freedom and you don't have it like axis aligned according to X, Y, Z, so you can add this rotation equivariance to the representation. I hope it answered your question, but yes.
Okay, I have trouble visualizing this, but can maybe talk about
yes.
it. Yeah.
Okay, I can talk about it in the end.
Can I ask a question? Can I ask a question?
Of course.
So you compare to 3D 3D grid, and did you mean surface meshing or volume meshing when you compare it to 3D grid?
Maybe I didn't understand the question. Can you repeat?
So you compare to 3D grid. I mean, yes, efficiency of volume representation. So did you mean the grid over the surface? I mean, meshing over the surface or over the volume?
So over the volume, right? Because you don't have, how can you define a volumetric grid around the surface? You can think of like our representation is a way to define kind of like a volumetric grid that is more densely around the surface.
But you don't see anything inside the surface, right? So you don't need you don't need volume meshing. So and the surface meshing is well developed field, let's say in boundary and element methods, as opposed to finite element methods. So probably it would be a good idea to compare with that.
To what? Maybe I'm less familiar with that.
To surface meshing, 3D surface.
So I'm like I think I'm less familiar with methods that did this, but like think of like our original data are meshes, right? And as I said, it like kind of like in the introduction that I made, working with these meshes can be a bit difficult, and we want a way to, by giving these meshes, to make it like a representation in another way. Maybe there's like a way to, I don't know, maybe mesh all of the surfaces and all of the data to be in a kind of like unified way, and that I'm not less familiar. But yes.
Search for boundary element methods, and you will find a lot of references to surface meshing. It's a well-developed field which was developed already long ago. So probably it will give some value to your research.
Okay. Yeah, well, definitely. Thank you for thank you for the reference. I will look it up. Okay, so just like going back to this to our representation, so we have this representation which we call X, and you can first of all see that it is like a tensor. So if you think of like a point cloud, which is n by 3 tensor, so ours is like n by m, which m is like n by d, where d is like the number of variables that we have for each one of these volumes. And we need to define a global function, right? So the global SDF is defined as the weighted combination of the local evaluated local functions of each one of the grids. So let's go over quickly on this equation. So first of all, given a point in space, we want to evaluate its local function evaluation according to each one of the volumes. Right, so think of like a point, I don't know if you see my cursor, but think of like a point that is in a region that is overlap between two ones. So you can evaluate the local function using trilinear interpolation according to one volume and also to another. And then you want to kind of like combine these two values, and you do that by weighting combination. And we simply choose a very simple weight function, like a step function, as a weighting, and this will give us the final SDF approximation, again as a weighted combination of each one of the evaluation of the 3D position according to these local functions.
That's a bit okay. So we now let's say I want to, let me bring up my drawer thingy. So I want to evaluate this point signed distance function. And then I go ahead, I calculate first its distance to this guy. I take the vector to this guy, and then I scale it according to its scale, and then
so think of like you have this point in 3D, right, that you marked. And first of all, this translation and scaling take you to the local coordinates of this local function, right? And this operator is doing trilinear interpolation according to this volume of this point, like within a 3D grid. So it will basically.
What does that mean?
Trilinear interpolation. So like bilinear interpolation, or just like a linear interpolation between how can I draw myself?
So we just
interpolate between the values that are stored on these voxels, right? So in the volume itself, you have you have values, right? And you can interpolate between the volumes according to the appropriate proportional location according to this grid. So if I'm adding to your drawing, right? So you have SDF values here, 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 and here, right? This is VI is basically again an M by M by M grid that store these values, and given now this new value, you can interpolate the SDF according to this value. And in 2D it's called bilinear interpolation. In 3D is trilinear interpolation because you have 3-dimensional to interpolate with.
Then you weight it by the distance to the middle point, and
so think of like if you have a point. I don't have an example, but if you have a point that if you have a lot of overlap, you want it to have more effect of the SDF from the close, like where it lies more closely to the center compared to this one. So this point is kind of like equal, but you can think of like examples where you have like a different overlap, right?
Yeah. So we reconstruct by looking at what value is at our pixel, and then we weight it, or we take like a normalized sum of those values for all the let's say points, or all the local grids that contribute to that point.
Exactly.
Niall?
Yes, hello. So I have a question. So the point that Hannes had put on the grid, it was basically kind of similarly distanced to both the xi and so pi and pi plus 1 points, but the one in the middle has finer grid, so it's with lower scale. Wouldn't it make sense to have like higher weight in the sum for grids that are with lower scales, so they should be finer, have better
You mean
representation?
like you mean like a different weighting function?
Yes,
Again?
probably a different weighting function, giving more weight to points that have smaller scales. So currently, I see that we have a scale in the denominator, but this takes into account only the relative distance to the center. And basically, this point you have
So not
highlighted.
exactly, because you scale it, right? So if you,
Yeah,
because it's scaled, it is, right? It is, so you can think of like if I draw this function on 1D, it will look something like this, right? And
yeah.
if you have a smaller scale, so this function will be like shrinked according to the scale.
Okay, again, the point that Hannes has picked up, it basically is the same distance from both centers, pi and pi plus 1. Yes,
Yes.
because
Yeah, but
it's
it will be different according to the scale. Like even if
uh
this point has the same distance, like
yeah,
Euclidean distance, it will be different because it is like the distance is measured according to the scale. But
yeah,
I would say it's not the maybe it will be more clear in the next slide, but the choice of this weighting function will not vary taking it, it
okay,
won't really affect, and I will explain maybe like in the next slide it will be understandable, right, a bit more why. So something that is maybe important to kind of like to say here, because we only care about this global function evaluation, right? So even if you think of like this local function, even they can be non-SDF, right? But their weighting combination should be an SDF at the end, because this is the evaluation that we care about. And I will explain how we can, so this is the representation, and let me explain to you now how can I pre-process it, and given a mesh from the data set, given like a 3D shape, how can I make this representation to be a good approximation for our surface. Okay, so so we want to define the pre-process of M-SDF, right? So given a shape, given a surface, again, we are back to this car example, we want to output an M-SDF representation such that the global SDF evaluation that we have in mind will be a good approximation of the ground truth SDF of this shape. Okay, so this is our goal for the pre-process, right? And how can we pre-process? How can we make the M-SDF representation given this shape? So our stage, we have two stages for the pre-process. The first one is initialization. We want to have a good initialization for our representation. And first we initialize the centers points by simply lying point samples across the surface. And we can do that by sampling points that are farthest from each other. So we're gonna have like kind of like the most well covered points around the shape. So we do that by doing like farthest point sampling. So think of it like as like pushing the points out of each other in order to get a good coverage of the surface. So this will be our centers initializations. Now, given all of these points, we can compute the one scalar, which is like the minimal covering scalar. So we want the volumes to kind of like cover all of the shapes. Given all of these sampled points that we have from the centers, we can compute the scalar that is like the minimal covering according to all of these distances between all of the points, and we can initialize all of the volumes to have this same specific scalar. So this will define us the initialized size and like location of the volumes and their size. So as you can see from the right, this is like the points, the centers, and each one of the centers volumes. And now, given these volumes, we can initialize the local function, basically given the ground truth SDF. So as I mentioned before, right, where like you can think of like similarly as we had in the 3D grid. So you have point in space, and for them you can kind of like query what is the ground truth SDF. So think of like a single volume here, right? You know its resolution, you know its location, so you can only take the volumes, like the voxels on the grids, and evaluate on the points what is the ground truth SDF and store that in the volumes. Okay, so this will give you the initialization for the representation. However, if you evaluate how the zero level set of this type of a representation look like, this is what you get. So it is somehow similar to the initial curve, but it's not a very good approximation like we have in the goal. And the reason for that is you can think of like, okay, so each one of the local volumes is kind of like describing a local SDF, but because you have like overlapping and because of the inconsistency between like this volume is going to give you this specific SDF, and maybe according to the trilinear interpolation you're going to have maybe a wrong evaluation, so the weighted combination of them will not yield the proper SDF approximation as you have before. Maybe this can be yeah, you can think of like as here, right? So you have like bigger volume, bigger voxels and smaller voxels, and maybe a point here will not, so a point here will not have the same SDF approximation according to this to each one of the volumes, right? Because of the approximation of each one of the grids. So the weighted combination of them will not yield a valid and true SDF. Wait, I just need to go over this really quickly. Okay. So from that reason, so we have a very good initialization point for our representation, but it is not perfect because it's not approximating well the shape and the surface as we want. And because of that, we have another step that we call a fine-tuning stage, where we basically fine-tune and train the representation X. X is our representation, right? This is composed of all of the centers, the scales, and the volumes, and the local grids. And we can train it according to this loss of sampling points around the space and are very close to the surface. And we want that the SDF value, according to our evaluation, will be approximating the true SDF. So it is simply a regression loss to the SDF values of points that we are sampling around the surface. And because this evaluation of the function is differentiable with respect to this parameter, we can simply apply this fine-tuning stage, which is like, we do that, it's very quickly, we do that for like 1000 iteration, and we get this final result from the right here, which is a very good approximation of our surface. Okay, so, and as again, said again, all this process takes around a minute. So given a shape, we can pre-process it very quickly. And if you can think of like a large scale of like, I don't know, 1 million shapes, you can parallelize this process and do that on multiple GPUs. And, you know, sorry for the noise from the outside. I hope you don't hear it. And then you can pre-process the data set itself. So any question now? So maybe Daniel, for according to your last question, think of, because we're doing this fine tuning, the choice of the weighting function is less effective, because we kind of like, okay, so if the weighting function is not good enough, we can fine tune all the representation a bit quickly, like very quickly, that we have a good approximation at the end.
I have a question. So I sent you a link.
Okay.
So I don't know. Maybe triangulation is not good for you. But if you just click on this link, so.
I would prefer if we just talk about, let's just get to how we even generate this thing, and then maybe later on we can talk about some more meshing stuff.
Yeah. By the way, until when we have time, I'm not sure until like how long is that?
We're quite flexible, but
Okay.
also we want to release you at some point.
Yeah, of course. Okay, so now let's go to the generative part. So I would say the generative part will not be something very, very new from what we saw in images. And the main like heart of this project was, you know, was about the representation itself and what we can like which representation will be good for generative model. So this slide will be a bit more similar to what we saw in images, but for our representation now. So the first stage, in order to train a 3D generative model, we take the data set of shape and we transfer it to M-SDF representation. And as I said, we can do that parallelized on multiple GPUs, and it can be very efficient. And now, now, like our data set, our target distribution will be this tensorial M-SDF representation. Similar like we had images, now we have this type of data set. So now again, in order to train a flow model, so specifically we did like a flow matching, and we sample a point from the data set, which is an M-SDF representation, and we can also sample a noisy M-SDF. So think of just like a Gaussian noise, which is in the same shape, same tensor shape as our M-SDF representation. And you see at the beginning, it just like look like a noisy something because the points are sampled like around the space, and also each one of the volumes doesn't really make sense. And again, we can look at intermediate steps. So specifically because we are doing flow matching, the intermediate step is going to be the optimal transport conditional path between those. So it's simply 1 minus t x1 plus t x x naught. And this is going to be our intermediate xt that we define. And as I said, because our representation is like tensorial, if you're familiar with the transformer, so you can think of it like each one of the volumes are like a different token that you input to the transformer. So you have like so the sequence is like the length of like the number of volumes that we have. So you can fit this representation xt into a transformer and predict the next step towards the clean airplane as we see here, which is xt plus 1. So again, very similar to what we saw in images. Yes.
And now because we like all our tokens have the same number of numbers, right? So we
Yes.
just feed them through our feed-forward layers, and we literally just put 3D coordinates into our feed-forward layers.
Yeah. So if you're more also familiar with the papers that did like generative models of point cloud, so they also did the same, right? They had like a transformer as their model, and they used like but again, instead of like predicting a point cloud, we have like a point cloud with features. So this is like not only XYZ, it also have more feature which kind of like represent the local volumes. And maybe to answer the question from previously about the equivariance, so in order just like to make this transformer equivariance with respect to permutation of this representation, we simply can ignore positional encoding, like position embedding, right? Because we don't care about the order of the volumes, and this will make our transformer to be permutation equivariant to this representation. Okay, so now given that we train this transformer on multiple data sets and on some and also like on different timestamp, we can generate a new airplane by starting from a noisy M-SDF representation and simply apply iteratively our transformer and solve the ODE to get the final airplane predicted. Okay. Any questions?
Yeah. No, it's kind of cool that this works and that people.
I would say that
the...
like the fact. So one of the main motivation and the fact that we thought that it will work is because we saw many papers that did like point cloud generation that works pretty well, right? And again, so it's like, okay, if it will work for point cloud, if we just like add feature to each one of the points in the point cloud, why would it work? But it's nice that it knows kind of like to generalize really well between the different shapes, the different like parts of each one of the planes. But yes.
How many points do you have?
1024, which is usually what people have used for point cloud generation. So it is like a common like number of tokens that the transformer can be dealt with.
Yeah. So for proteins, we also do this point cloud generation thing, right? And the common thing since 1 or 2 years now, what everyone is doing, or what's more or less the state of the art, is that you have a point and an orientation associated with it. And then you like you also move around your points, but you also start from a Gaussian of points and then do flow matching to generate your point cloud. But people use some equivariant networks for this, like what's called invariant point attention, what AlphaFold also used for their protein structure prediction
You
stuff.
mean not like a transformer? You mean like instead of transformer another architecture, or for the rotation you need like a different equivariance?
Oh, this is ignoring the rotations. This is just a different architecture than transformers. It's like an equivariant transformer version. So it's also attention, and it's quadratic, but you have a notion of the orientation to the points that you're paying attention to, and you have a notion of orientation and distance of the points that you're paying attention to. And it's kind of cool that
sounds very heavy, no?
Yeah, exactly, right? And that's, I think, the main difference. That's here with proteins, we were most of the time dealing with something like 300 points or around that. Yeah, we can also like train bigger models, do a lot of gradient checkpointing and so on. And then there are these bigger models that can generate, or there are these models that can generate bigger proteins. but our quality of generated proteins becomes a lot worse for proteins with more than 300 points. But that's sort of enough for a lot of purposes. And here now, if we're moving to these more points, and we need more points, then I guess this just isn't sufficient anymore. You can't.
Yeah, I would say that I feel like all of the field is kind of like shifting to like big transformer, and as you just like enlarge the parameters of your transformer, it can generalize really well, and you don't so it sounds like you kind of like inject some prior knowledge into the transformer, right? Like according to your data shape. So you can think like that, like general vanilla transformer can learn this based on your data, right? The attention map according to some, I don't know, distance points is something that it can learn given like a bunch of data. So I would say like taking it to be more general, just like let the transformer to learn the attention layer and the property as it needs. I think it's like now more of the direction that all of the generative field is going towards.
Yeah,
but this is like as I see it.
Yeah, I'm not sure if for for proteins people have tried just generating points with a non-equivariant transformer, and then also generating rotations with this non-equivariant transformer. So what we've tried in our group, just because we had some setup and it was very easy to try it out quickly, was to also just do the or how do I? Was to also just have a non-equivariant transformer, takes 3D coordinates as input, predicts 3D coordinates, and then yeah, this looked fine, generated stuff that looked like protein. And
but
yeah,
you mean non-equivariance with respect to permutation or with respect to rotation?
Non-equivariant with respect to rotation and translation.
In translation, yeah.
But it also wasn't equivariant with respect to permutation, I think, which makes sense for proteins, right? Where you have an actual sequence of residues. And
yeah. I know, it feels like that today it doesn't matter what you give to the transformer, it will learn to generate. But I agree that if you have like a prior knowledge of equivariance, it can generalize a bit better. Yeah.
Anyway, then what do you want to? What are the slides that you have left, or what do you want to show?
So the one that we have left is just like results. I don't think we can very I think we can kind of like ignore them. So we showed like so here in this slide we just gonna show like other like quantitative results that we want to kind of like establish our representation as a good and valid representation according to the design principles that we have. So in terms of like efficiency of approximation according to parameter count, and also in terms of timing. But this is like very high level. And basically we showed the generative like generative results on two settings of two data sets, where the one is like class conditioning, right? So we have a data set that have like 55 different classes and of, I don't know, chairs, cars, and whatever. And we showed like class conditioning generation compared to other method, and we have the results here. I don't want to maybe dig into the technical details of the table from the right. If you want, there's like more information in the paper, but you can see that like we claim that we have like more sharper results than the smoother result that are in the previous works. Another thing that is cool that we did in this work is to do text-to-3D generation. So we have a data set of around 700 pairs of captions and shapes. And we show that we are able to do text conditioning generation. So I don't know if you can, so most of the examples here are pretty small, are pretty like easy and, short captions, and not something that maybe you are familiar with images. And this is because this data set size is not very enough for training such models. So usually people, when they're training like text to image generation, they use like around million or milliard of images, and like this is one of the downsides of text to 3D, that you don't have enough information, but still we're able to get some nice properties and like thin structure, like you see in the butterfly here, and some text understanding. Like I like this example of like 2 cupcakes, 3 cupcakes, and 4 cupcakes, and there is some nice versatile results here that I would say that is not very that is like for me, I think it's like a one step in order to get like a good and more versatile text to 3D generation.
Okay.
Yeah.
Good. Then thanks for, yeah, I think these look pretty good. I don't know how other 3D generative model generations look like, but yeah, I find this a little bit impressive. But do you know, are there some people doing just voxel based? I mean, here you're also generating voxels, so to say, right? But they're local voxels, and the voxels then have a signed distance function associated with them. Did you also, like, for example, maybe you even tried having densities inside of these, inside of your local voxels instead of distances? And do people do like then just
like a different, so density is just like a different representation, right? You can even represent a nerve. You can think of it as like using this thing. Because we focused on geometry, we think that like SDF are better suited for like geometry approximation than density, right? Because density, like you don't have a very straightforward way to get a density field and extract a surface out of it. And because we wanted to, given the SDF, there is like a very easy way to extract a surface out of it, just like by extracting the 0 levels. And but it's definitely a way to, another way to use the representation is doing like local volumes of densities. And in terms of like another, like the global 3D grid representation, there are some previous works that try to do that. For example, I think this work is kind of like a grid-based 3D grid-based representation. But if you think of, so for 2D images, you have, I don't know, people are doing like 64 by 64 generation, or maybe, I don't know, 128 to 128. If you think of like 3D grid, it goes cubically, and you cannot go above like 32 by 32 by 32. And you won't get a good, very well approximation. I think maybe there is some work that like did like 64 by 64 by 64, but if you're going to, I don't know, transformer or 3D convolution, you're kind of like limited by the size of the things that you can represent.
Aren't like the state-of-the-art image generative models, like I think EDM v2, for example, is maybe the current state of the art. They're all latent diffusion models, and now can't we have?
Yeah, and I think so. There is some work I can that we didn't compare it to because they don't have code, but they did like an SDF, and then like train a gridless SDF, and then learn like a latent encoder decoder to it, but still like the SDF, the global one, is like 128 as something like that resolution. And again, if I'm going back to the slide of like comparing the representation, you're gonna have like a lot of empty voxels. Eventually, the idea behind our representation is that we only want to store information on the surface itself, and it's redundant to have like SDF far away from the surface, like in the volumes, because you don't occupy this space at all.
Yeah, but like we're talking all the time about SDFs, right? Which makes sense because it's about your paper. But I'm thinking about volumes as well, and this or just densities and volumes, and that the inside of our object is also interesting because that is the case, for example, for proteins. And yeah, so you're saying there are some works that's, for example, or that found success by just auto-encoding a grid of voxels and then doing some latent diffusion stuff.
I think there are some works like that. I don't know where it is. I can send you some things. So you said that in protein you only also care about the inside of the shape. That's what you mean?
Yeah, like if you generate, if you're trying to generate a new protein, right, then you also have to know, or if you then in the end want to go ahead and synthesize your sequence or something like that, then you also need to know what the residues are on the insides of the protein.
Yeah. So again, I'm less familiar with this type of data, so maybe this will be less appropriate because in 3D shape, we only care about the surface itself, right? In order to represent the surface, we don't care about the inside or the outside. But maybe you can think of like another way to represent proteins that is more appropriate for you, because like it's gonna be as efficient as possible as parameters.
Then of course we are thinking about those, drawing inspiration from other people as well. Okay,
yeah, but in terms of like our representation, we worked with SDFs. Definitely, instead of like storing local SDF on each one of the volumes, you can store local volume density in each one of the volumes, right?
Yeah.
Just like representing different feature. It doesn't representing a different function. It won't be that much of a difference.
Good. Any other questions from other people in the room? Okay, Anton.
Yeah, hi. So quick question, how could you incorporate textures onto M-SDF?
Yeah, very interesting question, something that I actually also exploring right now. So think of like, as I said, that you can store densities instead of SDF. So think of like in each one of the volumes, you can also incorporate like a 3D texture field, right? So you have like a small texture field in each one, like so a texture field is like for a 3D point, it's predict the texture. So it only makes sense to do that on the surface itself. But if you have like a small volume, you can think of like, okay, a point that is close to the surface will have like a texture that is like of the closest point to it. And so instead of like the current volumes, which are like 7 by 7 by 7 by 1, and 1 is the SDF value, you can have like 7 by 7 by 7 by 4, which is like the SDF plus RGB channels that are stored within the volumes. So we can just simply extend our representation by just like adding a local texture field to each one of the volumes. I'm not sure it will be the most efficient way to represent the texture, because it will be a bit of like more, you maybe need to increase the resolution to get all the high frequencies of the texture, because like if you think of surfaces, it's more smooth than and locally it's more smooth, and in texture you need maybe to have like higher frequencies, but like this will be the most straightforward way to kind of like extend it to also include texture.
Okay, cool. And is it also suitable for kind of doing also other diffusion on top of the representation? Like you could combine it with SDS or?
Yeah, so given there are some works that you don't even think you don't even care about the SDS, right? There are some works that did like texturing over a given mesh. You just need to a way to define the UV mapping, and given a mesh, you need to I don't know, add texture to it. So this is something that can also be done in 2 stages approach. I think there is like a paper that is I can again let me know, and I will I don't know remember the name of it, but again, given a mesh, we'll add you do like text to texture conditioning on this mesh. I think it's texture diff or something like that, if I'm recall correctly.